And then on the other hand, we have infected and negative, which is going to be 1, since there is a 20% chance, and 20% out of 5, 20% of the 5 people is going to be 1 person. So if you have 100 Americans, 4 of them are going to be infected and positive, 1 of them are going to be infected and negative. However, we can also look at the uninfected and positive. So if there is an uninfected person, well then there's an 80% chance that they will test negative, actually. So there's an 80% chance that they will test negative, which means that there is a 4 out of 5 times 95. So 80% of these 95 people, so 4 out of every 5 of these 95 people, is going to test negative, which means that if we multiply 95 times 80%, or which is also known as just 0.8 if you want to plug into the calculator, then we will get 76, which is kind of a messy number, kind of a random number, but it emerges because 95 times 4 out of 5 is 76. So, which means that out of all the 100 Americans, 76 people will be uninfected and they will test negative. But there's also the 20% of people who will be uninfected and test positive. So the 20% of uninfected people who will test positive, which we can also do with a 95 times 0.2, which is just the same thing as which is just 19. Notice that both of these add up to 95. So out of the 100 people, we split the 95 group uninfected people and the 5 group infected people so that we can split them like this. And we split them into 2 pieces based on whether they test positive or negative. So anyways, after we figure out that after we figured out that there are 4 people who are infected positive, 1 person who is infected negative, 19 people out of the 100 who are uninfected and positive, and 76 out of the 100 who are uninfected and negative. So just keep in mind that we're just looking at, this is percentage, but we're also looking at it from the perspective of just random 100 people in the United States. So what this means is that if we just look at this, which is just the possibility that Jonathan, since we already know that Jonathan tested positive, we know that 19 there is a total of 23 people in the United States out of the 100 who would actually test positive. But only 4 of these people out of a random sample of 100 Americans would actually be infected. 19 of these people would be uninfected but test positive, meaning that there is an 80% accuracy rate. Even though there is an 80% accuracy rate, Jonathan testing positive, it's more likely that he will be one of these 19 people who were negative and actually tested positive, who were uninfected and tested positive. The test said that they were positive even though they weren't. The test is pretty accurate, but based on the fact that very few people actually had COVID in comparison to in the entire population during that time, it's actually very unlikely that he had COVID. So there was a 4 out of 23 chance that Jonathan was actually infected, which is approximately, according to the calculator, approximately a 17% chance that he was actually infected, or he is actually infected if we're in 2022. So does this entire thing make sense to everybody? Do you have any questions? Essentially, what we did was we took all of the possibilities that can be attained based on this information, and you find the chances of each of these. Because even though we mainly think about this versus this, we actually have to think about the actual chances of being infected if you're positive, which is this giant circle here. So this is actually a very important idea in a lot of statistics, because even if you have a test that is very powerful, a lot of times the test can actually have above a 99% chance of being correct. A lot of the times, even especially when you're doing studies or science, a lot of times because the chances of a person actually having COVID, or the chances of your test actually, of whatever you're testing being true, is so small, then your test actually has to be incredibly precise to actually know that once you test it as true, positive, that's actually that what you're testing is true, or the property that you're testing is true. So I think this is a just an introduction to statistics and a lot of statistical analysis ideas, but it is quite complicated, and I think it's just something to sort of think about. And without further ado, then let's actually begin our sort of game games that we prepared. So the first game that I sort of thought about was two dice. It's a very simple game. So in this game, I start by rolling a die. You then guess whether the second roll will have a larger or smaller value than the first. If they're the same, we'll just redo it. Um, but if you are correct, then you win this game. So what is the best strategy to win this game the most amount of time? So let's just say that you're playing this game like 100 times, right? Or 1,000 times. You're just playing this game and you want to win as many times as possible. So what is the best strategy to win this game? So if you just remember that a die has 6 different sides. Each side is basically equal. There's an equal chance of landing on either side, right? So what this means is that since there's an equal chance of landing on either side, then you basically guess. You don't know exactly what it's going to be, but there are strategies you can do to try to win this game. Because even in randomness, you can find probabilities. Even in equal probabilities, you can still know a couple properties. So let's start by actually trying this out. So here's just a standard Google dice roller here. And I will just simply roll this dice, and we get 4. So does anyone want to give it a shot? Like, just literally just guess. Do you think that the next number will be higher or lower? I mean, there's no stakes here. You just take a guess. Do you think it will be higher or lower? So, does anyone have any ideas as to you think that what you think like you can sort of think about to guess whether this is higher or lower? There aren't really any wrong answers here because technically speaking, it can be either way. Like you could get a 5 or a 6, or you could get a 1, 2, or 3, or you could get a 4, in which case we'll just roll again. But since we didn't, since no one decided to try to make a guess, we can just roll again and see what is more likely. So when we rolled again, we got a 5. So if we'll just sort of write this down as we started with the 4, we got a 5, which is going to be bigger. If it's a bigger, I'll just mark it down with a star. So then if we roll again, just to see what the chances are, roll again, and we get a 1, which is smaller. We roll again, just to try this over again, see which one is the most likely. We got another 1, another 5, got a 6, we have a 4, so we'll just re-roll and delete that. Another 4, 5, 4, another 4, 2, another 2, 3, and then another 2. Okay, so we're reaching the bottom of the page, but you can kind of see that it's actually more likely that it'll be smaller, right? It's actually more likely that it would be smaller because when you're looking at this, you have 1, 1, 5, 1, 1, 5, 6, 6, 5, 2, 2, 3, 2. So here we have 4 times that it was bigger, and we have 6 times that it was smaller. So 4 times that it was bigger, 6 times that it was smaller. Better? Okay. But this is a little bit, it's not a super big sample size, but we can actually see from this what the pattern kind of is. So the thing is that we can also look at all of the possibilities for each of these outcomes. So there are actually 6 different outcomes. There's an outcome that their second roll is going to be 1, your second roll is going to be 2, your second roll is going to be 3, your second roll is going to be 4, or it's going to be 5, or it could also be 6. It's a little bit in the corner. So actually no, let me go back. So there's a chance it could be 1, 3, 4, 5, or 6, and any of these are possible. All of them have an equal chance of happening. However, we know that these 3 are going to be smaller than 4, because 4 is just going to be there, as that's our number. But the only thing is that 4, there's actually a 0% chance of that happening, because every time we roll a 4, we just roll again. So we don't actually know. Like, 4 doesn't actually lead to anything, because we're looking at our end results, whether it'll be bigger or smaller. So if you roll a 4, then we're just going to roll again until we don't get a 4. So we can basically just ignore a 4, because even though there's a 1/6 chance that we'll roll that, we'll ignore it, because that's the rules of the game, so we'll ignore it. But on the other side, here, if we get a 5 or 6, it'll be bigger than our 4 that we started with. So that's a little bit. So it'll be bigger than the 4 that we started with. But what this actually means is that since we have 3 possibilities of it being bigger and 3 possibilities of it being smaller and 2 possibilities of it being bigger, and all of these are the same probability. They all have a 1/6 chance of happening, though if we have a 4, since 4 we ignored 4, they all technically have a 1/5 chance of being the final result. Which means that since there are 3 and there are 2, there's a 3/5 chance that it'll be smaller and a 2/5 chance that it'll be bigger. not because the die is not because the die is like weighted or anything. It's just literally based on the laws of probability and just how probability works. So what this means now is that we have a 3/5 and a 2/5 chance, but this is only if we rolled a 4. Well, what about if we rolled a 2 or something else? We can try a different one. Oh, it's another 4. But if we say rolled a 1, then let's look at our probabilities. Let's look at all of the possibilities that can happen. So if we rolled a 1, then it can be a 1, a 2, a 3, a 4, a 5, or a 6. And if we roll another 1 after this, if we roll another 1 after this, like 6, if we roll another 1 like that, oh, just say we've rolled another 1 after that, then we just ignore that, because if you remember, if we roll 1, then we just re-roll. So we can ignore that. But now look at all of these other possibilities. All of these other possibilities are greater than 1, which means that if you roll a 1, there's a 100% chance that your next roll, like if you follow the rules and sort of skip it, if we redo if they're the same, we redo, then it will be a 100% chance that it will be bigger, that the next roll will be bigger if we skip every time it's the same. So we have a 100% chance for 1, that it's going to be bigger, a 40% chance for 3, sorry, that's for 4. Then what is going to be, does anyone have any ideas about what 2 or 3 or 5 or 6 would be if we rolled those first? Such as, let's another one. Such as if we rolled a 5 first, like this, then should you guess greater or smaller? So remember here, this is a chance of greater. Chance of a greater second roll. Well, there's a chance of it being greater. There's a 100% chance of it being greater if it's 1. Then, of course, you should guess that it's going to be greater, that the second roll is going to be greater. And if you guess that it's likely going to be true, then you win. So if it's 1, then it's a 100% chance. But what about if it's 2 or 3? What are the chances of it being greater if it's 2 or 3, or 5 or 6? Or we can first look at 5 in this case. So does anyone have any ideas as to what the chance it would be bigger what the chances are of it being bigger if we roll a 5 first? So does Joyce or Jasper, do you have any ideas right now about what the chance of it being bigger is if we roll a 5? Okay, so what if it's a 5, then all we need to do is simply just we can simply look at the possibilities. So there's a possibility of being 1, 2. So Jasper says that it is 50%. So that is a good guess, because, well, it's a 5. But if we look at the actual possibilities itself, that is that is how we can actually figure out the chance. Because actually, if you remember before, when we tested 4, we got 6 less than, less, and 4 greater. So that actually makes a lot of sense, since there was a 40% chance, and out of our 10 rolls, we did 4 were greater. So, and 6 were smaller. Ignoring the ones when they were the same. But for 5, the sort of the right way to think about this, or the more like classical way to think about probability, is to just look at the possibilities. So if it is 1 to 4, then it will be less. If it is 6, it will be more. And if it is 5, then we re-roll, so we get rid of 5. Then that means that 4 out of 5 times it will be less if it's 5. Whereas 1 out of 5 rolls, it will be more. Or 1 out of 5 plays, it will be more. You will end up with, if you guessed more, 1 out of 5 times you would win. And based on this here, we know that 4 out of 5 is actually 80%, right? So if you multiply 4 out of 5, 0.8, which is 4 out of 5, by 100, then you get 80. So it would be an 80% chance. So 80% chance of being less, which would mean that there's a 20% chance of being more, which means that number 5 is actually 20%. So has this made sense to everybody? It's like, I'm not sure like if this is a standard standard thing that people learn in school, in middle school, but I do think it's quite important for a lot of people to know about, since it is, after all, like the world is, after all, a probability-based world. Okay, but if we notice, there's actually a pattern here. So notice how 100% it's 1, the chance of it being greater during 1 is 100% chance. And then for 4, it's a 40% chance, and for 5, it's a 20% chance. I think this pattern will be a lot clearer if we also calculate it for 2. So if we have 2, then 1, 2, 3, 4, 5, 6, well, it will be less if it's 1. 2 we can just ignore, since we remember the rules of the game say that if it's the same, then we redo. That is kind of arbitrary, but we just, it's sort of to simplify the game, to make it more just simple for people to play. But if it's 2, then we actually have 3, 4, 5, 6. So there is a 4 out of these 5 possibilities it's going to be more than, which means that there is an 80% chance that it is more. So for 2 is 80%. And right here, I can actually sort of tell that 3 is actually also going to be 60%. It's actually going to be 60%. Why is it going to be 60%? Well, because if we can notice a pattern here. Because as we move up, if say this was 3, then less would gain 1, since 2 is less than 3, and more would lose 1, since 3 has now become sort of the same. It's going to be the same as the first roll, which means that it's actually going to be 60%. That 80% already kind of looks like a 60%. But if we notice a pattern here, every time we go down, it's going to decrease by 20%. So And the reason for that is actually simply just because as we move up, the as our numbers move up, well, then the number of numbers that are more than that number, so number of numbers here that are more than one is way more than the number of numbers that are more than five. Since there's 6 is greater than 5, there's only 1 that's greater than 5, whereas there's 2, 3, 4, 5, 6 that are greater than 1. Which means that as we go up, as we go down, it will decrease in probability, and it will decrease by 20%. Which means that for 6, it's actually going to be 0%. Not only just because we're subtracting another 20%, 20% minus 20% is 0%, but also because if we're at 6, there's no numbers that you can roll here, since it's a 6-sided die. There's no 7 on this die that is greater than 6. So therefore, if you roll a 6, you should always guess that it's going to be less. If you roll a 1, you should always guess it's going to be greater the next roll. If you roll a 2, you should still guess that it's going to be greater. If you roll a 3, you should still guess that it's a greater. You should also guess that it's greater, but if you roll a 3, you're not as sure. It's like a 60% chance. If you roll a 4, you should guess that's smaller. If you roll a 5, you should also guess that's smaller. But generally speaking, if we just look at what you're supposed to guess, we know that 1, 2, 3 should guess greater, whereas 4, 5, 6 you should guess less or smaller. Larger or smaller, yeah. So based on this, we can also look at a different idea about how this works. So since we're here, all we care about is what's more likely, greater or less than. But the amount to which it is likely is actually quite important. And we'll see that in our next game, which is also about 2 dice. So in this game, it's the same game, but where we start by rolling a dice, you then guess whether the second roll will have a larger or smaller value than the first. If they're the same, we redo, but this time you bet some amount of money that you can choose. You can choose how much you want to bet, and that is actually a big part of the game. How much money do you want to bet? And you can bet the amount of money that you can bet. You can base that off of the amount that the second roll will be larger or smaller than the first. You guess whether the second roll will be larger or smaller than the first. If you're correct, you'll double your money, so you'll make more money, and if you're wrong, you'll lose your money. Okay, so that's an R. Correct that typo. But if you're wrong, you'll lose your money. So what is the best strategy to win the most amount of money in this game? So based on this, you can think about it. If you're more likely to win, you should bet a lot more money. Whereas if you're more likely to lose, or if you're less likely to win, then you should bet a lot less. You should bet less money. So if you know that, then it would actually be you can think about it as a way of calculating how much money you would likely earn from a given game. But that is quite complicated, but I think that just based on this, based on what we did before with the 20%, 100%, if there's a 1, there's a 100% chance of it being greater. 2, it's 80% chance. 3 is 60. 4 is 40%. 5 is 50%. 20% chance. 6 is 0% chance. Then which one greater? Then which one here? 1, 2, 3. Like, how much do you think you should bet, or which one do you think you should bet the most money on, given your confidence? Since if it's a one, you're a lot more confident that's going to be greater than if it's six. You're very confident that it's actually not going to be greater because it's a 0% chance of it being greater. So, does anyone have any ideas about which sort of which dice roll? Because you know what the first die is going to be. You know what the first die is going to be. So you will bet after the first die is rolled. So does anyone have any ideas as to how much money, or which one you should bet the most money on, if you, based on the probabilities, the possibilities of the first roll? 1, 2, 3, 4, 5, 6. So I'll give you a moment to think about it. And yeah. So we can look at our confidence level. If it's greater, if it's 1, then we actually know for a fact that the second roll is going to be that if you guess that it's going to be greater, then you're going to win. So if the first roll is 1, then you should actually bet as much money as much money as possible. You could bet all of your money. You should bet all of your money. But and it's the same thing if it's 6. Since if you guess that it is going to be less than, there's a 100% chance you're going to get that money. You're going to double your money. So you should also bet 100% of your money if it's 6. But if it's something like 2, then it's very likely. It's an 80% chance. I mean, even with the COVID test, 80% sounds pretty good for a COVID test, like how likely it's going to be correct. If you had an 80% chance of winning a lot of money, then you would probably take that. But 80% is not as good as 100%. So you would probably bet a little less money to sort of make sure you still have enough money left later. But if it's something like 3, if you get 3, there's only a 60% chance. There's only a 60% chance that your guess will be correct. Actually, for 4, it's also a 60% chance, since if you guess less than, remember you get to guess whether it's larger or smaller than the first, then you would also have a 60% chance of being correct. But for 3 and 4, it's not a very high chance of guessing correctly, which means that for 3 and 4 you should bet less than 2, which should be less than 1. And 5 would be the same as 2. So what this means is that the amount that you bet should be determined if you want to win the most money, or at least not lose a lot of money, by the chances of you winning. And we can actually test this in the dice game. So let's say that we start with so let's say that we start with a roll which is 4. Well, let's say that I just bet $1 here. If I bet $1 here, then on the next roll, oh, whoops. So if I bet $1 here, and based on this, I will guess that it's more likely to be smaller, since there's only a 40% chance of it being greater and a 60% chance of it being smaller. But I only bet $1, and it was smaller. So I doubled my $1 to $2. But now let's roll again for a first roll and a second round. So on this, now I have $3. And I think that this is very bad. So I would probably bet only $1 again, because there's only a 60% chance of winning here. You should save your money for the times when there's a 100% chance of winning, so that you can maximize the amount that you win and minimize the amount that you lose. And since you know that a 1 or a 6 is going to come, or, eventually it's going to come, then you should always bet higher on it when it's a better chance of winning. So, based on this, we can now roll again. It's a 3, and I will guess that it is greater, since based on the fact that there's a 60% chance the next will be greater. And it was smaller, so I lost all of this $1 that I just spent, and now I'm back to $1. I'm back to $1. But think about it, if I bet $2 on that, I would have lost all of my money. So you should go sort of all in when there is a very high chance, such as when you get a 1 as your first roll, or a 6 as your first roll, like what happened here. So if I get a 6 as my first roll, well, I'll go all in. I mean, if I had 1,000, a million, $1 billion, I would put every $1 billion, every single dollar, every single cent into this game, so I could double my $1 billion or $1 million, or even just $1 into $2, so that I would get $2 here. And I put it in, and well, of course, it's going to be something smaller because there's no 7 on a dice. Basically, what this is saying is that when you're betting in a game, you should always bet based on the confidence that you have, and you should guess based on the possibilities. You should look at all of the possibilities that can happen, and then you can determine that, and then you guess based on the possibilities that you have determined. So this is a sort of a, not basic, but it's a very conceptual understanding, like a logic-based understanding of probability and how you should act based on probability. And I do think that this first question is a very important question in terms of a lot of science. And I mean, if you care about this, or if you're going to study statistics or try to be a scientist, you should learn a lot about p-values and that kind of stuff, which are the chances that a scientist thinks that the results are actually correct or came out of not just random chance, or their confidence that it's correct. So, and even if you have a very high confidence, 80%, if the chances that it was correct in the first place are very small, or the chances that your hypothesis was correct was very small, then, well, even if your confidence level based on your test is very high, even if your test's confidence level is very high, and you test it correctly, you test that's positive, well, maybe it's actually a false positive. So basically, be skeptical of probabilities, and maybe in the future you could become an expert card counter. All right, that should be it for today. Thank you guys for attending. I have a runny nose, so yeah. All right, thanks. All right, bye.